Hey everyone, in this video we will talk about double integrals over general regions and not just rectangular ones. So let's look at the single variable and two variable cases here. So there's a little bit of a difference, right? So in the single variable case, we're always integrating over an interval. So everything always looks like the integral from a to b of some function, maybe it's in y instead of x, but it's always on a to b. And so when we look at two variable, thus far, right, we've looked at our domain and it's always been a rectangle, which allowed us to break it into, say, the integral from a to b and c to d of some two variable function with regards to x and y. The issue here is that not every region needs to be rectangular, right? We could easily have something that looks like this, where your x is bounded between a and b, but your y doesn't have a consistent bound, right? That's not rectangular. And so here, if we said this was, say, g1 of x, and this upper bound is the curve g2 of x, then we would translate this into a function or a double integral where on the inside we first integrate with that and we get a function out. So we put like g1 of x as our lower bound, g2 of x as our upper bound for y, right? So we'd have our f of xy dy, and then we would do our numerical x bounds on the outside. And so the fact that the first integral will spit out some function of x, which will then spit out a number after the second one, means that yes, we're still going to get a volume, it's still going to be a number, and everything's going to work out. And luckily, you've been prepared for this already when you've done area between curves and volumes of solids of revolution, right? You've already dealt with looking at functions as upper and lower bounds instead of just numbers. So let's look, for example, at the function here xy, right? But on the triangular region instead of a rectangular region with vertices 0, 0, 2, 0, and 2, 2 here. So this is our domain down in the xy plane. And we can end up viewing this in a couple of different ways when doing a double integral. So first, if you want to do x bound second, you can see that x is between 0 and 2, right? But then your y value is not hitting everything between 0 and 2, right? So we wouldn't do 0, 2, and then 0, 2. This would be the whole rectangular region from 0 to 2. And so what we want, right, we want to look only at this part here, right? And so what is this line? Well, this line is y equals x, right? And so the shaded region, our y values aren't hitting everything between 0 and 2 this whole time, right? We're limited to the fact that y is below the line y equals x, right? So y is less than or equal to x. And so this gives us our upper bound, okay? So we look at the y value below and we see, okay, this is my floor. And then when we look above, it's not looking at the highest point at 2, but rather looking consistently as you move along x to see what your upper bound is, right? So your upper bound is y equals x, and your lower bound is y equals 0. And so the real integral that we want is going to be the integral from 0 to 2 and of the integral from 0 to x of xy dy dx. So let's go ahead and look at how to actually compute something like this, right? So we've got 0 to 2, 0 to x, xy dy dx. So we do have to be careful with our order here, right? So we do very much want the one with the variable bound on the inside, because if we have that on the outside, we're going to spit out a function instead of a number for our definite integral. So it has to go on the inside, and we want only numerical bounds on the outside. And then, well, we just go ahead and do the integral. So this first one is with respect to y. So we get xy squared over 2 from 0 to x dx. And then when we plug in x, right, we're going to get 0 to 2 of x cubed, right, that's going to be x squared there, over 2 dx. And then when we integrate this, we'll get x to the fourth over 8 from 0 to 2, and that's going to give us 16 over 8, which is 2. So this would be our volume here. And it didn't necessarily matter that we chose to do x there. So let's look at the alternative, So if we look at this same picture, but from a different perspective, then we could say, okay, my y bounds are from 0 to 2, but then what's happening with regards to my x bounds, right? So x here, just like y was less than or equal to x is going to be greater than or equal to y, right? That's what's getting me this region. And so if you wanted to do it the other way, you would do 0 to 2 for your y, and then for your x, well, your lower bound, right? So your x has the lower bound, x equals y, and then the upper bound is x equals 2. And so this would be from y to 2 of the same function. And so your first exercise here, I want you to show that you actually get the same result, right? So obviously, if we can write it both ways, we should be getting the same result both ways. So I want you to compute this and show that this also equals 2. So let's look at another example. So here we want the volume under this paraboloid, x squared plus y squared, and above our region R, so usually we're just gonna, we know the height and it's gonna be involved in our integral, but we're mostly concerned in terms of the setup with the region in the xy plane. And so here we're going from, we have the bounds between x squared and 2x, and so we would, set those equal to each other. We see that we get x equals 0 and x equals 2 as our intersection points, right? So we see x equals 0 here and x equals 2, so this is 2. This is going to be up at 4. And so our domain here, our region R, is this shaded region here. So let's think about how we actually want to set this guy up. So again, if we're looking for our upper and lower bounds, so in this case, again, let's start with like x. So x is going from 0 to 2. And so there we would have to look at our function bounds for y, right? So y has the lower bound given by the bottom curve, right? So this is y equals x squared. And so x squared is its lower bound. And then on top is y equals 2x. So that's our top function, right? These would be like our g1 and g2 of x. And so the integral that you would set up is going to be x from 0 to 2, y from x squared to 2x of, your x squared plus y squared dy dx. So that's one way to do it, right? And we'll just stop with the setup there. Again, the actual integration works out pretty similarly, although this time, of course, you have to worry about x values in both of your bounds. But it's also worth setting up this equation going the other direction, right? So what if we want to look at y from 0 to 4 up here? Then what are our x bounds, right? So then our x lower bound is going to be this guy. So this is y equals 2x, and so that means x is going to be y over 2. And then my upper bound, so this is my upper, so we go from y over 2 to y equals x squared, and so x is, well, in this case, the positive square root of y, right, because x is greater than 0 there. And so an alternative way to set this up would then be the integral from 0 to 4, and then we'd have y over 2 to the square root of y, x squared plus y squared, dx dy. And this is useful to be able to go in either direction because sometimes you will find it much easier to integrate with respect to one variable first instead of the other one. So for your second exercise, I want you to set up the double integral for this integral over the region R, bounded by y equals the square root of x and y equals x squared in the xy plane in both orders, right? So I want you to do the dy dx, and I want you to do the dy or dx dy version. Okay, so this is just practice setting it up. You don't have to actually compute it. Okay, so just set it up. All right, thank you for watching.